Welcome to Full Momentum, an HEC-RAS podcast. I am your host, Ben Cary, and here joining me today for episode 19 of our Full Momentum series is Chris Goodell. Chris, it's been a couple months. Hope you had a great holiday season. Happy New Year. We're in 2022 now, which is pretty crazy.
Yeah.
How you been?
I've been good, and Happy New Year to you too, Ben. It's been a while. I wasn't sure we'd ever see 2022, but not disappointed to leave 2021, that's for sure. Things are good, yeah. Keeping real busy, as you know, with work and everything, and all the family activities going on. So it's all good. How are you?
I'm good, man. Yeah, not a whole lot of complaints. We've had a nice kind of stretch of weather up here in the Northwest for January at least. So
Yeah.
enjoying a little bit of sunshine where it presents itself. But excited to get back into the vodcast groove in 2022. It's crazy that we've done almost 20 episodes of this now, but pretty cool.
Yeah, let's keep it going. And speaking of weather, yeah, we had some pretty wild weather between Christmas and New Year's here in the Portland area, and really the whole Northwest of the U.S. Some snow, which is sort of rare around these parts, at least down in the valley where we live. And then it all melted, and we got some rain, and we got some flooding. So that was exciting too. Nothing major, but just a lot of local flooding, and some of the creeks were up and going over roads, and that's always fun for us hydraulic engineers to see and drive around. I always like to stop at bridges and check and see if the water's hitting the low chord of the deck, and see if you can see any scour or anything like that. Very nerdy stuff. Yeah, my family hates it when I do that. But, hey, it doesn't happen all too often.
Pulling off on the side of the road whenever you see flooding. That's got to be fun.
Yeah, for sure.
Now, Chris, I couldn't help but notice it looks as though you're trying to compete with me in the facial hair department.
I got a little bit of some growth going. I will say right now, Ben, I will never try to compete with you because I don't think I could ever get there. It's a struggle for me to grow this thing. It's all patchy and just, I don't know. It's very itchy too. I don't know how long I'm going to last, but I don't know. I started it after Christmas when I took that entire week off, and I just got lazy about keeping up the shaving. And then next thing I knew, I was like, maybe I'll keep it going. And it's a thing. Well, it's not going to last.
I like it. It looks like, although it does make you look like you've been, troubleshooting a really, really complicated model, and it's giving you a lot of fit. Just kind of let the facial hair go as a result of it. So
yeah, I was hunkered down in a cabin in the remote wilderness trying to solve a RAS model, and shaving was the last thing on my mind at that point. So
that's great. So another quick question for you here as we start the new year, Chris. I'm going to throw kind of a curveball at you a little bit. So obviously everybody this time of year has, New Year's resolutions they've come up with. Most of them are usually related to maybe what you eat or how often you're working out or things you're doing with the family. But I want to put you on the spot and ask you, what is your HEC-RAS modeling New Year's resolution for this year?
Oh man, I thought you were just going to ask New Year's resolution in general, but this is a HEC-RAS. Okay, HEC-RAS related. Well, I'm going to have to come up with one because I didn't officially make one.
So let me go first, and then while I'm giving mine, you can come up with yours. So my New Year's resolution for HEC-RAS modeling this year is going to be to listen to what I tell folks every time that we teach one of these 1D, 2D RAS classes, and that is start simple and then add detail where needed later. It's one of those things that we tell people all the time, and I found myself in 2021 too often jumping in and adding complexity to models that I didn't know I needed, but maybe assumed I did, and it ended up just causing headaches down the road. And so my resolution for this year is I really want to do a good job of starting simple when I'm building out a model. With the understanding that I'm likely going to add complexity, maybe even some of the same complexity that I think I need at the start of a model. Wait to do it until I know that I need it, because that's always such a good thing in terms of just kind of overall model progress and the such. So what is your 2022 HEC-RAS resolution?
Oh man, that's a great question, and I like your answer a lot. Practice what we preach, right?
Yeah, exactly.
But no, it is a really good habit to get into. Start off simple, and it will pay dividends in the long run. I think for me, being put on the spot here, I want to get deeper into the theory behind all the computations, computational hydraulics. It's been an area that I've always kind of had I feel like a surface level understanding of the computations, but not a granular level understanding. And I want to get really deep into it. And in fact, I was doing a little prep for this podcast on some of the stuff we're going to be talking about. And I was getting a little bit into the theory, and I actually found myself reading one of Danny Fred's old papers on the 4-point implicit solution scheme, which is what HEC-RAS uses. And I was finding that this is tough reading, but if you sit there and you focus and read it like 2-3 times in a row, you can kind of get it and understand it a little bit better. And so that's what I want to do. I want to learn that theory at a lot deeper level and be able to explain it to others, and more importantly, be able to explain how an understanding of that theory can benefit you in how you set up your model, but also how you troubleshoot it. I mean, we talk about that stuff a lot in our class and when we're helping others do HEC-RAS modeling. But I'd like to be able to get into a deeper level and be able to explain it, because it is computational hydraulics. I don't know about you, Ben. It's tough for me. It is the math involved is really high level stuff. And it's not stuff I'm used to. I'm much more comfortable on the practical side, the user side of the software. But I think it is important to know that, at least at some level. So there you go.
And there's a lot of, I think, new computational hydraulics and theory to learn about the new 6.0 release or 6.1 release of HEC-RAS. There's a lot of improvements that have been made. And I think you and I both have a pretty good understanding of the practical side of what those improvements mean and how to apply those. But I think there's some theory to be learned. So that's a good one, Chris. I like that.
Yeah. Maybe we can do a theory podcast at some point and put everyone to sleep. It'd be good sleeping material.
Exactly. Cool. Well, we have a very cool episode today for everybody who's tuning in. We're going to talk about some recent landslides / dam failures that have occurred in Brazil, and kind of some video of that, and maybe even mix in some HEC-RAS applications to that. We're also going to talk about the computation options and tolerances window of HEC-RAS. We're going to get into kind of the theory of it. And yeah, so it's going to be a really cool episode. Before we get started, though, let me go ahead and give a shout out to our sponsor for today's episode. We're thankful to be sponsored by our firm Kleinschmidt Associates, who is known throughout the industry as a firm that provides practical solutions to complex problems affecting energy, water, and the environment. You can learn more at kleinschmidtgroup.com. So thank you, Kleinschmidt, for sponsoring today's video. Also, before we get going, I just want to make a quick plug for our upcoming 1D, 2D HEC modeling class that we have starting on February 23rd. This is going to be a 6-week class. It's going to be the same format that we've been doing for, the last 2 years. So it's 6 weeks, 1 lecture a week on Wednesdays. It's a 4-hour lecture. And then in between lectures, we have an opportunity to actually take what we've learned in the lectures and apply them to RAS projects with what we call workshops. So it's a really good opportunity to learn HEC-RAS, learn 1D, 2D modeling. The class is really meant for a wide spectrum of different abilities from a user standpoint. If you're just barely getting to know RAS, it's a great class to get you up to speed, give you a bunch of tips and tricks as you learn and grow into that hydraulic modeling role that you have. If you consider yourself to be a pretty high level modeler, it's going to give you kind of additional information that's going to take you to that next level and maybe challenge some of your thoughts and your preconceived notions on how to best do 1D, 2D modeling. So it's a really great class. We've had some great success with moving it into an online platform. So if you're interested, go to kleinschmidtgroup.com under the Knowledge Hub tab, and you can actually sign up for the class there. You can also visit Chris or I's LinkedIn page, and we'll have shared the registration for that class as well. We do only, I think, have 15 spots left for this upcoming class, so it's filling up very, very quickly, which is good for us. But if you're interested, make sure you sign up very, very soon. The next class won't be for a few months, so if you're interested, do that now. Anything to add to that, Chris?
Yeah. What are the dates again? February.
Yeah, February 23rd through March 30th, and I would assume that that class will be full probably in the next 2 weeks. So make sure you sign up soon if you're interested. With that, let's dive into some technical talk. Chris, I believe you have a couple cool videos and maybe some Google Earth imagery to share with us. So I'll turn it over to you.
Okay, yeah, let me set the stage a little bit. So there's been some recent very heavy rains in Brazil, and I understand it's projected or forecasted to continue for a while. And I was tipped off by a friend and colleague, co-author of mine, Pedro de Laura, who's from Brazil, and he sent me a few videos of some pretty amazing hydraulic events that happened recently. And so I want to take you to this place in Brazil. It's in the state called Minas Gerais. I think I hope I pronounced that right. I don't know if I did, but it's Portuguese, and I don't speak Portuguese. But anyway, Minas Gerais, or Gerais, is a state in Brazil, and the name literally means general mines. So there are a lot of mines in this part of Brazil. And so I'm going to zoom into one called Pau Branco. And here we go. So this is the Pau Branco mine. And as you can see, there's a lot of activity that's been going on for a while there. This, unlike what you may have heard recently, some of the failures that have happened in Brazil, this is not from a tailings dam. In fact, this is an iron ore mine, as I understand it. And I don't know a lot about this, so forgive me if I get some of the details wrong. And please feel free to comment if you know more about this than I do. But as I understand it, it's an iron ore mine, and they dry stack the material versus disposing it in a tailings pond or tailings reservoir. And so you can see all of these lifts, these dry stacks here. But, and this is my guess, is that they have this retention pond here because there's probably minerals that leak out or other toxins that leak out of this dry stack when it gets rained upon, and they want to capture that and keep that from going downstream into the watershed. So this is kind of a capture reservoir to capture all the toxins, and then ultimately let those settle out before the water is able to spill and continue on down into the watershed. Now, as a dry stack, you would assume, okay, well, we don't really have to worry about dam failures, right? Because there's no reservoir with all the material being dumped into. And as you may recall, there was this failure a few years ago, the Brumadinho Dam, which was a tailings dam, and this one was pretty spectacular. As you can see how quickly the entire dam gave way, and this is what you get with a tailings dam failure.
Yeah, I believe we covered this topic on much earlier episodes. So, yeah.
Right. You can see the devastation, and several people were killed, and just untold amounts of damage downstream. You can see the sludge and slurry moving downstream. But that was a few years ago. So the one I want to get into today is here at Pau Branco. And notice this reservoir right here, this detention pond, and then the dam that's retaining it right here. So I'm going to play you a video, and this is what Pedro sent me of what happened here. Now, when I first saw this, I thought, oh, there must have been some maybe upstream dam failure or just a massive rainstorm event that caused this. Because if you look closely, you can actually see the flood wave progressing through the reservoir here. It's incredible. It's very well defined. And as it approaches this dam, you'll see water start to increase through the spillway here. And then ultimately the whole thing's going to overtop here in just a second. What's incredible here, though, about this is a very, very short duration event, which got me wondering what caused this when I first saw this video, because I knew nothing about it when I first saw this. But here you can see we've got some overtopping here. You can see some dark material over here on the left. And so that's important. Now we got a lot of overtopping. The entire dam is being overtopped with a tremendous amount of flow. And you being a dam break modeler, and you are too, Ben, you know, what would your thought be here? It was like, mine was, yeah, like, so this dam is going to go.
Exactly. You shared this video with us on Friday, and as I was watching it, I was just waiting for a breach to form, because that amount of overtopping, especially considering the fact that it has a bunch of, looks like there's some woody debris, some heavier material. I am just completely shocked that it didn't, cause a traditional breach over the top of that crest. But to the credits of, the contractors and the engineers that designed that retention dam, it holds somehow, which is really, really phenomenal.
Yeah, it's amazing. And you can already tell it's starting to recede, the flood. So this is a very, very short duration flood. I mean, at most a couple minutes, right? And so my initial thought was, well, this must have been a dam failure from somewhere upstream, because, how could it be such a short duration storm that would cause this? And so I did a little bit more investigating and got some more information from Pedro in Brazil, and he showed me this other video, which actually gives us a little clue to what happened. So this is the dry stack area behind the reservoir, upstream of the reservoir. And so it turns out because of the heavy rains, there was actually a massive slide, and this slide went into the reservoir. So this is not a dam here. This is just material stacked up. But there was a slide here that went into the reservoir. And here you can see the upstream end of the reservoir. This is just what's left over afterwards. And as it kind of pans downstream, you can start to see, here's the spillway from that dam that we were looking at before. And look a little bit closely, you can see the top of the dam right here. Everything is filled in behind it with sediment and sludge and mine waste and all that, right? And notice the road right here was very much overtopped. In fact, there's another video showing cars and trucks out racing the flood as it was happening on that road. And then it continued on downstream. Here's the cleanup afterwards. But now we kind of have a better understanding of what actually happened. Here it is looking in the upstream direction. There's the dam right there. There's the slide. And so now I want to go back to this, and I'm not going to play the whole thing, but I want to start it again. You can see the slide material at the upstream end. And what it's doing is it's literally pushing all of the water up and over the dam. It completely displaced the entire reservoir. And so even though this this dam didn't breach, the dynamic effect is still the same as if it did, maybe even worse, because all the water was evacuated. It just, instead of going through a breach, it went over the top of the dam. It's quite incredible to see this.
So, Chris, as I'm watching this, first thing that comes to mind, especially considering, the forum that we're on today, is this something that you could model using HEC-RAS? Obviously it's something you could certainly model using a 3D model. I think I've actually seen landslide models incorporated into a software like Flow3D, for instance. But how would you do this if you were, wanting to represent this in a 1D or a 2D model?
Yeah, that's a great question, Ben. And before I get into that, you can see the slide material right here, the dark portion, and it's just pushing all the water up and over the dam. But yeah, to get to your question, the first thing a lot of people think about is in something like this, we need to simulate mud and debris, non-Newtonian flow here. But I would actually step back and say maybe not, because this water is being pushed out from the slide material. So I think it's sure you've got sediment entrained and mixed in, but I think it's acting a lot like water. It's not like what you would get necessarily out of a tailings dam, like what we saw from Brunadinho. So I would model this as straight up water. But how do we simulate this event? So I think the best way to do this would be to set up a stage hydrograph at the upstream end of the reservoir and simulate the wave created by this slide displacing the water at the upper end of the reservoir. So essentially that's what it's doing, is it's creating what's called a mega tsunami that progresses through the reservoir and then up and over the dam. And so what you could do is you could kind of estimate the volume of material and how much water is displaced and maybe turn that into a stage hydrograph and use that as your upstream boundary. And then just run the model and let that water go.
Yeah, it's really interesting. Do you have any for folks that maybe would want to do this? Using a stage hydrograph makes sense to represent that wave. Any tips on maybe how to develop what that stage hydrograph would look like, even if it was rudimentary or a little bit coarse?
Yeah, I think you could probably try and get very scientific with it. But in reality, it's probably going to be a very coarse exercise. But if you could come up with the kind of the initial mass that's sliding into the reservoir and somehow estimate that volume or the sectional area of the wedge coming in, you could then consider that water being displaced maybe straight upwards. And what does that turn into as far as a stage? If you take that volume and then divide the wedge area, that gives you a height, right? And so that could be translated into a stage hydrograph. And the timing, of course, is very quick on this. As you can see how fast this event happened. I don't know exactly what it is. And, I would also get in touch with my favorite geotech who specializes in landslides and say, hey, what do you think? How would we simulate this? So we can maybe talk to our buddies at Cornforth or some of the other firms and see what they think about it. As they are experts in landslides. I'm not.
Yeah. So maybe a multidisciplinary approach to coming up with what that would look like.
Yeah, exactly. So anyway, it's a pretty dynamic event, pretty tragic, and it's too bad that these are happening. The rain is just picking up incredibly. So hopefully they'll get a handle on this quickly and we won't have any more of these events happening in Brazil or anywhere really. But, for dam safety purposes, it's a good idea to predict and understand the consequences of such events like this. And one way to do that is through a HEC-RAS model and model it, see what happens.
Yep. Good stuff. Well, that's really cool, Chris. Thanks for sharing that today. I'm not sure if everybody was aware of this because it wasn't nearly as big of a deal. There wasn't as many fatalities as with other, dam breaches that have happened over the last couple of years in Brazil, but it's a pretty unique failure mechanism. So I think it was worth touching on today. All right, Chris, let's get to today's technical topic, which is going to be all about the computational options and tolerances window. This window is something that a lot of modelers don't necessarily open up very often. They might not know all of the different options that are available to them, but I would argue that it's one of the more important features of HEC-RAS if you're really going to take your modeling expertise to that next level. This is also a topic that we cover in depth in our online 1D, 2D HEC-RAS class. So if you guys are interested in learning more about this topic than what we're going to cover today, which is going to be pretty brief, highly encourage you guys to sign up for that because there's a lot of value to be gained from learning all of the different options that are available here. So Chris, I'll turn it over to you to kind of walk through these, the different options.
Yeah, and I agree with you totally, Ben. This is a very important part of unsteady flow modeling that I'm going to be talking to you about. And it's not to be dismissed. There's some things that you don't really have to worry about, other things you really want to think about. And there's some things Ben has saved our models recently. In fact, some of the projects that we've worked on, some of these computation options and tolerances. So yeah, the way you get to it is from the unsteady flow analysis window. and you go right down to the middle where it says Computation Options and Tolerances. If you're doing unsteady flow modeling, whether it's 1D or 2D or combination 1D, 2D, you need to get in here. You need to understand these settings. And when we first open it up, notice there are 5 tabs across the top. There's the General tab. These are mostly 1D centric, but not entirely. Then you've got your 2D flow options. You've got a few 1D, 2D combined flow options. There's the advanced time step control, and then 1D mixed flow. So we're going to kind of breeze through a lot of these and touch on some of the high points. Again, like Ben mentioned, if you want to get more information about this, there are the manuals, of course, but we get into much more detail and depth on a lot of these in our 2D HEC-RAS class that we teach.
Yep. And the reality of the situation is we can talk about them all we want. The only real way that you understand how valuable these are is to use them and figure out when to turn on some of these options, when to adjust some of these options. And that's just going to be through practice. So,
yeah. So let's get into this. So the first one you see here is the theta, implicit weighting factor. And you can see that you can apply a different theta for your warm-up time if you have any warm-up time. Notice over here we have number of warm-up time steps. If it's 0, then you don't have to worry about this theta because it's not going to be used. But if you do have some warm-up time steps, you can use a different theta for that. Now, what is theta? So theta is just a weighting factor in the implicit solution scheme, finite difference solution scheme that HEC-RAS uses for 1D reaches. And this is, again, right here, notice this box that says 1D unsteady flow. So this is only applied to your 1D reaches. So what theta is without getting into too much theory, and this gets back to my New Year's resolution, Ben, is to understand this stuff better. But here's how theta works. So when RAS is solving the equations, here we have the conservation of mass at the top and the conservation of momentum, and Ben and I get into this in good detail in our class and tell you what all these different terms mean. But notice the differentials in here. Okay, you've got your time-based or temporal derivatives, and you've got your spatial derivatives. dt is temporal, time-based, dx is spatial. When you have 2D models, you have a dy as well you have to deal with. But for your spatial derivatives, RAS will actually determine those derivatives that's used in the computations by evaluating the derivatives at discrete locations around and discrete time periods around it. So if you look at this box plot, this is also called the box solution scheme because it looks like a box. But you've got your spatial direction on the x-axis, and on the y-axis represents time, okay, t and x. So when you're solving for your spatial derivatives, RAS will actually consider those derivatives at the next time step as well to some degree. And the degree to which it considers those in the solution is this theta weighting factor. So it weights how much of the next time step influences the solution at the current time step for your spatial derivatives, okay? What is a spatial derivative? Well, convective acceleration is a spatial derivative. It's the change in velocity with respect to distance or space. That's a spatial derivative. So when it's evaluating that in the computations, it looks at this weighting to see how much it weights the next time step, n+1, with the current time step. Okay, now you can get into a lot more on the theory behind this, and we could talk all day long about it. And in fact, I'm not prepared to talk all day long about it because it's a very complicated mathematical problem. But if you do want to read more, get into the hydraulic reference manual, and I think it's chapter 2 where it talks about the solution scheme that's used for 1D. So you can read more about that in the hydraulic reference manual. But also I want to highlight this paper by Danny Fred, which is really all about what's being used here. So if you want this, you can find this online. Just Google this title here, Numerical Properties of Implicit 4-Point Finite Difference Equations for Unsteady Flow by Danny Fred. And in here, it talks all about what I just covered in a few minutes. So if you want to learn more about that and what theta is actually, from a theoretical standpoint, is, you can do that. Now, from a practical standpoint, theta equals 1 means you have a solution that is stable, but not necessarily the most accurate from a computational theoretical standpoint. Theta equals 0.6 is the more accurate but less stable. So you've got a range of values you can use from 0.6 to 1. Now, how we recommend using theta is you start building your model with a theta equal to 1, so it's nice and stable. And then when you get your model running and everything looks good, it's nice and stable and robust, dial that back and see how close you can get to 0.6. And that is the actual suggestion in the manual. Now, in practice, a lot of people leave this as 1. And I don't necessarily think that's a bad thing, Ben, but because there's a lot going into a regular river model that affects stability more than theta. And in fact, theta can be completely kind of overwhelmed by other issues in your model, like cross sections being too far apart, or your time step being too big, or too much change in cross section shape, things like that, you know. So, but for practical purposes, build your model with a theta equal to 1. Try and dial it back to 0.6 if you can. All right. Next one, tolerances. This whole section here, I recommend you don't touch. Leave it as the default. If you're doing an SI model, this will be a different number. Here we're using a US units model, US customary units, and so you see it's feet. But this is a tolerance in the solution. RAS, in order to solve these equations I just showed you right here, these partial differential equations, conservation of mass, momentum, RAS has to make some guesses on some of the parameters, because it actually uses the result in the solution. And so it has to guess what the result is, solve the equation, then compare the result to the guess. And the difference between those is an error. And that error is tracked as RAS iterates through the solution. If that error is greater than this number, then RAS considers that not a valid solution, and it will continue to try to get the error below that number, and it's going to iterate until it does. And this is the number of times it will iterate to try and get a solution below this tolerance, or the error below this tolerance. 20 times by default. You can change this number as well.
Yep. The water, particularly with the water surface calculation tolerance, I know that is sometimes a go-to for folks that are having issues with water surface elevation errors. They'll bump that up to the maximum value for stability purposes, and really to get their model to run faster. And in certain applications, I would say that's okay. For instance, if you're doing a dam breach model where a few tenths of a foot difference in water surface elevation is not going to make a huge difference, that's probably okay to do, especially if you try to ramp that back down by the time you have a stable model. But for some other detailed modeling or design level modeling, you're going to want to keep that tolerance low or at the default for situations. So
yeah, and here's why I recommend people leave this as is at this low number, even though it might be tempting to bump it up higher, is because what is an instability in RAS? An instability is just errors that have gotten out of control and they grow and oscillate versus diminish over time and space. We want errors that diminish over time and space in our models. We don't want them growing in time and space. Well, if you use a larger tolerance here, you're accepting more error in your solution. And if you accept more error, that error is more prone to grow with time and space versus diminish with time and space. So I've found very little success in improving an unstable model by using a larger number here. Now, if you want to speed it up, maybe, if it's hanging out on some errors that are pretty consistently just above 0.005 or something, and the model is what I would call stably unstable. So it's not really unstable, but it's putting out a lot of errors. You might try bumping that up and see if it'll speed it up, but it's not likely to get rid of an instability issue. So just a heads up on that. You can also control the tolerance on storage areas as well as flow. So RAS can track the error in flow as well. Now that's optional to have a number in there. You don't have to, but you can. And then this next one, the max error in water surface solution 100. This just gives an exit ramp for RAS if it's just going crazy and the errors are getting out of control, but RAS is able to keep going through it. It's not crashing yet. Having this number, maybe even making it lower, 100 feet seems awfully high for an error. If I had an error of 100 feet, I would want RAS to stop. If I had an error of 10 feet, I would want RAS to stop usually. So you might think about lowering this, and all that's going to do is it's going to crash it faster if your model is crashing. So you don't have to waste time watching it chug through a bunch of large errors. So let's move over here to this side. We've got the warm-up. Warm-ups are nice because if you have some initial conditions issues at the beginning of your run, running some warm-up will allow you to kind of work those initial conditions errors out of the solution before you get into your actual simulation. So think of this as like some negative time added on at the beginning of your simulation of constant discharge, just to allow it to kind of settle out before you get into your actual run.
Yeah, particularly nice for quasi-steady models where the timing of a flood wave isn't an impact. You're really just going to be trying to extract your solution when your model's reached equilibrium, and it's a classic quasi-steady situation. So warm-up time is especially helpful in those situations.
Yeah, and keep in mind though, you won't necessarily see this output, the warm-up time step or the warm-up period output. There is a way to turn that on. So you have to find that in the output options. But a lot of times I just like to keep that warm-up time as part of the actual simulation. Then I can see it happening. But sometimes you don't want to see it. Maybe if you're displaying a hydrograph plot for your client at the end, you don't want to have all this bouncing around happening in your hydrograph. So then you would use the warm-up.
Particularly with, again, if we go back to the quasi-steady idea, sometimes you're going to be displaying maximum value maps. And if you're simulating a quasi-steady situation, there's no reason to display values for lower flow values, for instance, because that's not what you're trying to model. So,
yeah, exactly. Next one are time slicing. So you can actually adjust your computation interval right here by using time slices. Now, why would you want to do it here versus doing it on the unsteady flow analysis window right here? Oops, you can't see it, but there's our time step. This time slicing, though, is actually tracked to the inflow hydrograph. So it doesn't give you a lot of information right here, but this time slicing doesn't happen automatically. It happens if, let me get out of this really quick, if on an inflow hydrograph, let's just pick one of these inflow hydrographs. If you've ever wondered what this time step adjustment options is right here, you can check this box and give a max change in flow, and RAS will monitor the change in flow on this hydrograph for every time step. And if that change in flow is greater than the value you put in here, then RAS will go into your computation interval, and it's going to slice it based on what you have here. And so here you can have a minimum time step. So in other words, I don't want a time step below this level, and I only want to slice it this number of times at a maximum, so you can have some control over it. Otherwise, RAS is going to continue to slice your time step until that change in flow on your inflowing hydrograph is less than that value you put in the box.
It also comes into play if you're adjusting your time step based on a cron number, which we'll get to in the advanced time step control. This restricts that as well. So it affects a couple different areas. So.
Yeah, so this again is only tied to your inflow hydrograph and only used if you've got this box checked and a value put in here. And again, only used if your change in flow is greater than that value that you put in there for any given time step.
So Chris, if you don't have that box checked and you have advanced time step control, and you're adjusting your time step based on a Courant number. And let's say that you reduce that maximum number of time slices to 5, but based on the Courant number advanced time step control criteria that you specified, it wants to slice it more than 5. You're saying it will?
Absolutely, yeah. So this advanced time step control is completely different and separate from this. This right here is strictly tied to inflow hydrograph if you have that box checked. This is just a different additional way of having time step control, because notice here you've got control if you're doing it based on Courant number of steps below minimum before doubling or maximum number of doubling. So here you have control over the amount of doubling or halving or slicing, if you want to call it that, that you do over here. So that's similar to this maximum number of slices, but totally different, two totally different things. In fact, this has been in RAS for many versions, way back into the version 4s, maybe even earlier, whereas this advanced time step control, I think, is new to version 5, I believe.
So what you're saying is the advanced time step control specifications would trump what you actually put in here. If your Courant condition required more slices than the maximum number of slices, then that would override basically this.
I don't think it's an override. I think it's more of in addition to. So I think what RAS first, and I'm not 100% sure on this, but I think RAS will monitor that inflow hydrograph and it will time slice accordingly. That gets you to a certain time step computation interval. Then it's going to look at advanced time step control.
I see. Okay.
And if you do it by Courant number, it's then going to run the simulation, evaluate the Courant number, and if it's too high or too low, then it's going to adjust your time step further beyond that original. Yeah.
That makes sense. Okay.
Yeah, really all kind of complicated stuff. I rarely ever use this. In fact, I don't know if I've ever used it for a project. I've done it just for fun before, just to test it out. But rarely ever use that. So I would spend more of my time in the advanced time step control. Moving on, we have these stability factors and decay exponents. By default, these numbers are not what you see here. So these are not the defaults. I think it goes 1, 1, 2, 1, I believe. They're not all 1 by default, but in any case, kind of like the theta, a value of 1 is the most stable, the most accurate, but the least stable. A value of 3 is the most accurate, the most stable, but the least accurate. Now, again, like theta, with a well-built model, if your time steps are correct and cross-section spacing, all that node spacing is good, you're probably not going to see much of a difference. However, there are some cases where you'll get oscillations and you have to bump this up to 3 or some higher number just to get your model through those oscillations. And so what we have here are stability factors for both lateral structures and inline structures. So if you have flow over one of these kinds of structures and you're seeing some oscillations, first of all, make sure your time step is good. That's the most important thing. But if your time step is at a reasonable level and you're still getting the oscillations, try bumping this up to a value of 3 for lateral structures or for inline structures. Now, if you have a lot of submergence at one of those structures, a weir or a gate, you can also get oscillations because of that submergence, that high degree of submergence. And so this is another way of dampening out those oscillations by using a higher number here.
By the way, Chris, the default is 2, 1, 1, 1.
Okay, so it's 2, 1, 1, 1. This one is the bald eagle data set, and it's got a weir, so it was bumped up to 3, probably to get rid of some oscillations.
Yep.
Yeah, so this is a really easy thing to try out. So if you're seeing a lot of instability or oscillations around a structure, what I'll usually do is I'll just bump all these up to 3, but you could target them if you wanted. Keep in mind, too, that this is 1D, 2D unsteady flow options. RAS will actually use this for SA2D area connections that have oscillations. It'll use the lateral structure flow stability factor, and it'll use the weir flow submergence decay exponent as well. If you have a gate, it will use this. So this is not limited to lateral structures and inline structures in a 1D model. These are used for 2D models as well.
Yep. So like Chris said, if you're having stability issues over a lateral inline structure, or if you're having a significant amount of submergence over a weir gate, bumping these up to 3 can be a really good place to start to get your model stable. And then again, once you have things, once the model's running well and you're happy with how things are performing, that's when you want to come back in and try to drop these back down to get the most accurate solution possible. So
yeah, awesome. And hey, this is kind of a new thing too, gravity. You have control over gravity. We used to not have control over that. Now we can control gravity. And gravity finds its way into a lot of the equations used in HEC-RAS. And so if you want to do some modeling on, say, Mars, not that this is the only parameter you would change, but at least you could get the gravity correct for it.
Just to clarify, Chris, that's just control over gravity in the model. We're not actually controlling.
That's right.
In the real world, so.
Yeah. If you start coming out of your seat, though, be careful.
RAS is powerful, but not that powerful.
Right. Exactly. I'm going to skip over this because this is a topic we could do for, we could spend the entire podcast on that. So I'm going to skip over this. Let's go to 2D flow options. First thing you'll notice is we've got 23 different parameters to deal with. So there's a lot more than what was in version 5 of RAS. So version 6 adds a lot more to it. We have a column called default. These are the default numbers that will be used for every 2D area that's added in your model. Now, if you open up a RAS model, you haven't done anything, you haven't added any geometry to it, and you change these values, now every 2D area that's added after that will adopt whatever default values you have over here. Okay. Most people just accept what's in here by default. And then when you add in a 2D area, you can go through and change those if you'd like. And so every 2D area you add will show up as a new column here. So here we've got 3 different 2D areas, and they can all have their own parameters. We've got theta in here. So theta is used for 2D modeling. It's the same thing as 1D. It's just used in the 2D solution instead. Water surface tolerance, again, same thing we had in 1D. Notice that the tolerance is a little bit greater though for 2D areas. Okay. There's a volume tolerance as well and a maximum iterations. Just like for 1D, I would recommend you do not change these. It's usually a fool's errand to get in here and try and change these to stabilize a model. If your model's crashing, it's usually not because of these settings, it's something else. And so,
one thing to note, Chris, I had opened up the computation options and tolerances window on my computer, and the default water surface and storage area tolerance in the general tab is actually 0.02, which means that this is actually lower for the 2D options than it is for the 1D. So.
Oh, okay. My bad. Yeah, good catch on that.
Yeah, just so for people know.
Yeah. And again, just to reiterate, this is a U.S. customary units model. These numbers will be different for SI models where you're using meters. Yeah, the equation set is quite possibly the most important thing in here by default, and there's a lot of debate about this out there as to whether this should be the default or not. But HEC has elected to make diffusion wave the default equation set. Now, Ben and I talk a lot about this in the class. So if you want to hear more about these different equations, definitely sign up for the class or get into the manual and read it. But you have to decide what equation set you want to use. Do you want to use diffusion wave, or do you want to use one of these full momentum or shallow water equation versions? The shallow water equations are going to be more accurate, but they're also going to take longer to run, and they're going to be more prone to instabilities. The diffusion wave is a simplification of your full momentum equations that you see here, the ELM and the EM. And it does not include your acceleration terms. Remember those derivatives we were talking about, the spatial and temporal derivatives? Those are actually omitted in the diffusion wave version of the equations that are used. So this has a very limited applicability range, diffusion wave. And we'll talk a lot about that in the class. But if you want to change it, and you should consider this for every 2D area, whether you should do diffusion wave or shallow water equations, this is how you change it. Shallow water equation, for most rivers, most modeling applications, you're going to use this ELM. EM is more for near field. It's a stricter solution on momentum, but not really needed for most riverine applications. All right. And we got initial conditions time, similar to warm up, but this is initial conditions time is segregated to individual 2D areas instead of warm up time is for the entire model. So this gives you another option for setting up a good initial condition setting for your model.
Yep, and I'll add to that initial conditions time and ramp up fraction, both of those components are really, really helpful when it comes to managing a 2D model, and especially sometimes a 1D, 2D model. So if you want to learn more about kind of how to maximize the applicability of both of those tools, that's another one of those things that we touch on quite a bit in the class. And so if you're interested in learning more about that, definitely sign up.
Yeah. Number of time slices. So here's another way we can slice our computation interval. In this case, it would just be for individual 2D areas and their respective solutions. So you could take the time step of 30 seconds that we have, and if I change this value to 2 instead of 1, it's going to use 15 seconds for the computation interval, but just for this 2D area. Yep. And so this is a good option if you have differing cell sizes and you're trying to meet your current numbers. If there are smaller cells in 193 versus 194, you might need a smaller computation interval. So you could slice this up a little bit to get that. Turbulence model. By default, it's not used, and it won't be used if you use diffusion wave. You would have to use one of these shallow water equations for the turbulence model to be used. But if you want to, you can choose from conservative or non-conservative for the turbulence model, and then you have the option to put in different mixing coefficients for both longitudinal mixing as well as transversal mixing. It used to be that you had one coefficient, and then in version 6, they split it up into transversal and longitudinal, so you could use different, because as the default numbers imply, the longitudinal mixing is a little stronger than transverse by default. Now, what numbers do we use here? Well, it's very broadly defined in the 2D HEC-RAS manual. If you open up your 2D manual and search on eddy viscosity or longitudinal mixing or something like that, you'll see some suggested values for your mixing coefficients. And they're very broad. This is the kind of thing that if you're going to use it, you probably want to calibrate if possible. If you can't calibrate, at least do a sensitivity analysis and understand how changing these values affects your results. This Smagorinsky coefficient was added just recently in a recent, I think in 6.0 or 6.1, and it's just an additional type of turbulence that can be included in. Again, read up on this in the manual if you want to know more and what values are typically used for that. Next one down is the boundary condition volume check. This one, it can be a lifesaver in projects, but basically the way it works is if you've got water flowing from one 2D area into another, whether it's from an SA2D area connection, or maybe you've got a 1D reach flowing into a 2D area over a lateral structure, if you start running out of water in the upstream feature as water's flowing through, and it turns out that for a given time step, there's not enough water to supply the volume that was calculated to leave that area over the structure, then you can actually dry it out and you can create errors and oscillations that could crash your model. This volume check will monitor that, and it won't take more water out or try to take more water out than it has. It kind of dampens it out a little bit. So this can be very valuable if you have, say, a dam break where you're draining a reservoir and you run out of water upstream of the dam, but it's still trying to pass more water than's available for a given time step. This will help to dampen that out.
Sounds familiar, Chris. It's almost like we were just working on a project.
Yeah, Ben and I had a project where this was a lifesaver. I mean, it really did save our rear ends on a model that was crashing, and we just couldn't get around it, and this did the trick. So it can be very helpful. Coriolis is not usually a big deal in most riverine models. It's mostly has an effect on really large bodies of water. So I would say most riverine applications, you probably don't need to use Coriolis, but maybe on really big lakes, reservoirs, bays, those kinds of things, you might consider it. But the bottom line is it's easy to try. It's easy to add in if you want to. All you really need to do is put in the latitude of your project. And if your project spans over, a wide range of latitudes, then maybe do an average. But this will only be used under three conditions. One, you put a value here. Two, you use one of the shallow water equation sets. And three, you check this box up here. So make sure you do all three of those things if you want to use Coriolis. And then, you can see if it makes a difference.
It probably will. It probably won't. Newsflash.
Yeah. I suspect it won't. Yeah. Exactly. So next we have the solver cores. So when RAS is actually computing, going through the computations, it is set up to distribute tasks to multiple computational cores or multiple processing cores on your computer. If you're lucky enough to have 8 cores on your computer, or even more lucky to have more than that, you can make use of those cores to speed up computations, because then it will be doing a lot of these computations in parallel versus sequentially on a single core. And so this can speed it up. It's more beneficial for really large models, especially large 2D areas where you have hundreds of thousands or millions of cells. That's where you're going to see some benefit in using a lot more cores. With really small models, it can actually be a detriment to use more cores, because it gets to a point where you've got diminishing returns, where you're spending more time distributing tasks than the benefit you're getting from distributing those tasks to multiple cores. So this has been set in this particular model to 8. I usually go with the all available and let RAS do that. If I have a really big model, a lot of cells, I'm talking hundreds of thousands, maybe millions of cells, I might evaluate if different cores does better. And if I have a really small model, I might actually try using less cores and see if that's faster.
This is becoming more and more of a, I guess, unlocking a possibility for some modelers, given how influential cloud computing has become in hydraulic modeling. And I assume that as more and more engineers and hydraulic modelers are using cloud computing, where you can actually have access to computers that have a lot more cores than a typical laptop or desktop computer has, understanding how cores affect models, especially really large models, is going to become more and more important. I think that's an area that modelers are going to kind of grow into in terms of their understanding.
Yeah, and if you do have one of these supercomputers that has 16, 32 cores or more, keep in mind that using all available may actually result in a slower runtime than if you use some lesser number of cores, because of that fact, that point of diminishing returns. And so definitely test that out before going all available. If you have a lot, if you have 8 cores, model. Yeah, if you have 8 cores or less, all available is probably going to be fine for just about anything you would model. But more than 8, you get into the large number of cores. Yeah, you want to evaluate that. All right, next one is the matrix solver. So we used to not have control over this. It was Paradiso or nothing, or Paradiso is your only choice. Now, if you hit this drop down, you've got this SOR, which is an iterative solver, and you've got this FGMRES-SOR. I was trying to make some kind of a word out of this acronym, like FGMRES, but that just sounds too weird. So bottom line is, build your models with the Paradiso. It's going to be the more stable one. Once you've got a good stable model, you may evaluate whether these make it run faster, because in theory these will go faster, but they may not be as stable either. So give it a try, but honestly, I think most people, Ben and I included, just stick with the Paradiso usually. Now, if you use one of these other ones, you'll have to figure out what parameters you're going to use down here for restart, iteration, relaxation factor, your preconditioner, iterate, whatever the heck that means. I don't even know what those things mean. You can probably get into the manual and read about it, but if you want to change it to the FGMRES, you've got these other parameters you've got to put in here as well. And here's a little bit of a bug. If you click this drop down and then go off of it, sometimes it goes away. But anyway. All right, let's move on. 1D, 2D options. There's not a lot in here, but this can be extremely important. And in particular, the first cell here, the maximum iterations. If you've got 1D, 2D direct connections, or this actually, despite the name of this, actually works on 2D to 2D connections over SA2D area structures. Okay, so I wish they would change the name, because this is not only for just 1D to 2D connections. But if you're seeing some errors there, your model's crashing right around a 1D, 2D boundary, or at an SA2D area connection that's connecting up to 2D areas, try adding some iterations in here, because as those two areas, whether it's a 1D reach and a 2D area or two different 2D areas, they have to share information at every time step. So the respective sides of that boundary are sending information back and forth at every time step, and they're sharing data like stage or flow. And if what's being passed from one side to the other is not matching what one side wants it to be based on its own computations, you get these errors, and these errors can build and oscillate into an instability. So having some more iterations will help to get rid of these errors. So these iterations are actually iterations happening at the sub time step level. So these are within a single time step, you get iterations at these boundaries.
I'll add, Chris, to that, that oftentimes folks, as a default, will bump that maximum iterations up to 20, just because they figure that they'll be able to arrive at a solution, and maybe the model doesn't crash when they do that. However, in my opinion, that's really like putting a Band-Aid on a really bad flesh wound. A lot of times, having those maximum iterations or any number of iterations can help you identify maybe what's going on with a particular 1D, 2D connection or an SA2D area connection. But ultimately, you need to be able to drop those iterations down to something that's much more manageable in terms of just runtime. So again, I always recommend, adding some iterations if you're having that really quick model crash at a particular area and you're not able to dissect the results around that connection to figure out what possibly could be going on, what you need to adjust. Because most of the time, not all the time, but most of the time that you're having a model crash around an SA2D area, there's underlying issues besides it just not being able to iterate. And so adding those iterations can help you identify what those problems might be, but then you're going to want to drop that as those iterations back down as low as you can go, simply for runtime. So that's just something I see quite often, is you'll have somebody who sends us a model that the model runtime's taking forever, and it's because they have this maximum iterations bumped up to some crazy level and they haven't fixed the underlying issue at that connection.
Yeah. And guess where we talk a lot about some of these underlying issues and how to fix them? That's right, in our HEC-RAS class. We get into
I promised everybody listening this was not meant to be a plug for the class the whole time, but it is the reality of that class, is we do go into depth on some of these things. And Chris, that's a good point. A lot of the unsteady computation options and tolerances are, they're good options to help diagnose a model. But ultimately, if you have a model that's not constructed correctly and you have some of these underlying fundamental issues, you can adjust these options all you want. It's not going to really affect, how well your model runs. You got to fix the underlying issues first, and adjusting some of these parameters can help diagnose that. So.
Yeah, and like Ben said, if you have 20 in here and it's using all 20 iterations, it can really slow your model down big time. So you may dial it back a little bit and accept some error above this tolerance. And as long as your model, maintains stability throughout that, come on, 0.02 feet error, that's not that big of a deal. You might even think about bumping this up, but again, remember what I said about that, the tolerances and accepting more error. So there is a balance there. Just be aware that this will significantly slow down your model if it's using these iterations. You'll see it just chugging, take forever.
Especially with a low time step.
Yeah. All right, speaking of time steps, let's get into the advanced time step control. Now, the first and default option is the fixed time step. It's just going to use whatever you have here on your computation or your unsteady flow analysis window. So notice 30 seconds here, 30 seconds. If I change it here to 1 minute, and then I click OK, that will change to 1 minute as well. So these two things are linked together. They're the same. Now, there may be a case where, hey, I've got a model, it's taken a long time because I have to have a really small time step, but a lot of the run is there's nothing going on. There's a lot of steady kind of flow happening. There's, maybe you've got a long period in between flood events or whatnot. And you don't need the really small time step for the entire run, but only for during the peaky or flashy parts of your event. So you could come in here and you can do it a couple ways. You can monitor and adjust that time step automatically based on the Courant number. So as your velocities decrease, your Courant numbers will come down, and that will allow you to get away with a larger time step to bring that Courant number back up to, say, a value of 1, which is a good target. Okay, so you can have RAS automatically monitor this. Now, keep in mind, to know what the Courant number is, it has to run through the computations, right? So RAS will actually run the computations, evaluate Courant number at every single computation node. If any of it is greater than the maximum Courant, then it's going to decrease your time step. It's going to cut it in half or slice it in half and rerun that computation. So you can imagine this, just like having your 1D, 2D options iterations turned on, can slow your model down significantly.
Yeah.
So, yeah. And so, go ahead, Ben.
In my experience, when I first started using the advanced time step control, the adjust time step based on Courant number seemed like a really, really attractive option. It's like, hey, my entire stability of my model is based on the Courant number, and Courant number is the most common reason why 2D models crash. So I can just use this and that'll fix all my problems. But again, this didn't really end up that way. Like Chris said, oftentimes if you're using this and your model has underlying issues, you're like you're using cells that are just way too small, you're going to end up with a model that's so slow, or you're going to have instability and issues, and now you don't know whether it's tied to Courant number or other potential issues in your model. So in my experience, adjusting the time step based on Courant number is not as nearly as helpful as adjusting the time step based on a time series, because like Chris said, if there's a particular point in time that there's a lot of action happening, like a dam breach or maybe a really large flood wave moving through the model, adjusting it based on the time in the simulation is a lot more of a controlled way to say, hey, I know that at this period of time I'm going to have really high velocities, so I'm going to go ahead and drop my time step down, and then I'm going to go ahead and increase that back up once that flood wave passes or whatnot. So it's a lot easier to control and understand what's going on, as opposed to just throwing in a maximum Courant number and hoping the model works. There's a lot less control and less understanding of what's actually affecting your model's computations.
I'm with you on that 100%, Ben. Yeah, I agree. I would much rather use the time series of divisors where you specify what the time step should be at a given period during your model run. That way RAS doesn't have to spend extra computational burden trying to figure this out. You do it yourself. Yeah, good point. But feel free to try it and see for yourself. But I'm either in the fixed time step or using time series of divisors most of the time.
Yep.
All right, finally we get to the 1D mixed flow option. So as the name implies, which is we've learned, it doesn't always mean it's just 1D on some of these things. But in this case, this is only for 1D mixed flow options. And a lot of people are under the misconception that this will allow you to compute super or subcritical or mixed flow, so super and subcritical flow in your model run. That is not the case. This is actually a stabilization technique that's built into HEC-RAS that is used when you get close to critical depth or greater than a Froude number equal to or greater than 1. So critical depth is when your Froude number is equal to 1. Greater than 1 means you're supercritical. Less than 1 means you're subcritical. Most rivers are going to be in the subcritical range, and you don't have to worry about this. Now, one of the areas or one of the applications of RAS where this is very important and is almost always used is in dam break modeling, because at the front end of your dam break, you can get some slight oscillations because there's a lot of acceleration happening there, a lot of local acceleration. And that huge amount of local acceleration can cause errors that can cause your model to crash. And this always happens, or I shouldn't say always, but it predominantly happens around a around a Froude number equal to 1 or critical depth. And so what RAS will do is it will actually monitor your Froude number when you have this used. And when your Froude number starts getting closer to 1, as you go across this chart here, it's going to multiply the acceleration terms, also called the inertial terms, in your momentum equation by this factor. So in other words, if you get to a Froude number equal to 1 on this chart, it's going to zero out those acceleration terms. Okay, and that's going to help stabilize your model because those acceleration terms are what go a little bit wacky when you get close to a critical depth. And so if you see a model, if you have a very steep wavefront moving through your system, and you see that wavefront moving and it goes unstable when it gets to a certain location, this might be the solution to that. This might be what you need to stabilize that. Additionally, if you see a model where you've got a lot of your reach showing up at or near critical depth and it's crashing, then try mixed flow. Now, I would also submit that if you've got a lot of your reach that's at or below critical depth, you probably don't have high enough N values because most rivers don't flow at or below critical depth. But that's for you to decide there. But using this can help out a lot. And it's really easy to try to. You just simply check the box. Now you do have control over these parameters here, but I usually leave the defaults and I just check this box right here and try it out. If it works, great. If it doesn't, then you're moving on to other things to try and troubleshoot.
And Chris, feel free to push back on me on this, but I would always tell people when it comes to the 1D mixed flow that it's kind of a last resort. Try to fix it with best modeling practices when it comes to using a higher Manning's N value, good cross-section spacing, other things that aren't going to, because again, you're lowering the accuracy of your model by using this mixed flow. And so if you've done all those best practices and you still don't have any success, then using this can be a good option. I'll also warn folks that there are certain agencies out there, I won't name names, but if they see a model that has mixed flow checked on, there's a good chance they're not going to accept those results. And so you just need to be aware that, again, the idea of this is to make your model more stable, but you are giving up some accuracy when you do that. And so, I would always recommend if you're going to turn this on, try everything you possibly can to fix the model once it's working. Identify if there's other issues going on, and then try to turn it back off. If you're still not having issues, or if you're still having issues, you may need to keep it on. But just people be aware that it's not a go-to for every single project.
Yeah, and it's there's a lot of opinions out there. I might not be quite as strict as you've been on mixed flow, and a lot of that is because I do a lot of dam break modeling, and
that's fair.
And it is there are most dam break models, especially very flashy, quick developing breaches, there's just no way you're going to get it to run without mixed flow on. But that being said, I never start my model with mixed flow on. I turn it on if I need it, but I don't turn it on if I don't need it. So I think that's good perspective there. Cool. Yeah, awesome. Well we got through it.
That was a great conversation, Chris. I think it's going to be super valuable to folks that are listening in. Again, if you guys can believe it, we actually spend even more time discussing this in our class, and I think we give some more insight into how to use these tools effectively. We'll give everybody a chance to actually practice using them in workshops, which again is the best way to learn kind of the power of the individual tools and whatnot. So highly encourage folks to sign up for that if you want to learn more, or do your own research into the hydraulic manuals that are come along with RAS, because they do a decent job of highlighting that as well. Before we dip out today, Chris, I know that you wanted to make a quick plug for an opportunity for folks to learn HEC-RAS in person with you coming up this year. So you want to talk more about that?
Yeah, so I've got a class coming up in May. It's specifically the week of May 9th. I think the dates are actually May 10th, 11th, and 12th. And this is going to be an in-person class on 2D modeling, very similar to the class we do online, but it's going to be more focused and it's going to be more intensive. It's going to be over 3 days instead of spread out over 6 weeks. And the cool thing about this class is it's in France, Aix-en-Provence, in fact. And so if you've ever wanted to do some training overseas, and you can talk your boss into it, or maybe you live in the area, you're in Europe, and you listen to this podcast, I would love to see you there at the class. If you want to sign up or get more information, let me show you where you can do that. So you go to Surface Libre is the name of the company, and they're hosting the class. My buddy Arnaud Coach, sorry, I'm awful at French, but Arnaud Coach, hope I said that right, Arnaud. Anyway, he's organizing it. He's my local person there setting this up, and this is his company, Surface Libre. So go to his website, and you'll see at the very right-hand side, HEC-RAS Seminar May 2022. That's the one. Scroll down here, and you can see more information about how to sign up and what we're going to be talking about. So hope to see you guys there. And another thing I want to mention, too, is we talked about some of these dam failures, in particular the Powell Bronco event that happened last week. And I don't have all the information, so I apologize in advance if I messed any of that up. And certainly if you know more about it than I do, please add that intel in the comments so that we can get the record straight. But I'm more interested in these events and, how they can be modeled in HEC-RAS. And I think we had a pretty good discussion on that. What do you think, Ben?
Yeah, I think that was great, Chris. Awesome. Well, thanks everybody again for joining us today. Appreciate you taking the time. Hopefully we'll have another good 2022 of podcasts and different topics. As always, we're always considering different topics to discuss. So if you have particular interest in a topic that we haven't covered yet, leave that in the comments of the YouTube video, and we'll try to get to that sometime this year. But with that, this has been Full Momentum, an HEC-RAS podcast. Until next time.